live on a screencast, and we're looking at this question. It's on page 17. We're in the IB review packet for this screencast. For those of you that weren't there, this is a question and answer session that we're doing on Monday, getting ready for the test that's on Wednesday. And we've been talking about some of the questions here. We spent some time on this one particularly, so you might ask your classmates if this one's still confusing to you and you weren't at the screencast, they can help you out with that one. But we're jumping all the way to page 17, and we're going to ask and answer the questions related to this. I think one of the first things to realize is what the axes are. So for the axis, when they put time here, it's a lot easier to understand. And that's not what they did, right? They have put, yeah, talk to me. Can you see the screen or not? Okay, I guess I'm going on. I'm unsure if there's a problem or not. I'm hoping that you guys are hearing me okay. This shows at time equals 0, a screen, like a frozen image of the wave. And then this is later at time equals 0.2 seconds, a frozen image of the same wave. And so what we're looking at here is at one minute, or at one moment, and then at a later moment. And hopefully not that long afterwards. And so now they're going to ask us some questions once we understand that. But if this is frozen in time, that means these particles, if this is a wave on a string, then this is going, this is clearly going to be going down in a minute because this direction of travel is to the right. This particle right here is going to be going down as this part of the wave moves to the right. This part's going to be moving up. This part's going to be moving up. This part's going to be moving down, because in a moment, you have to think of this entire wave as shifted to the right slightly in a moment from now. So this particle has to move down because this origin will soon be here. And this particle has to move down to be there. So this particle is moving down. In any case, the amplitude is just this distance here. Okay, which is what they ask. So if we look at the questions they ask, we'll jump back and forth. They ask for the amplitude. So the amplitude is going to be this distance, which is 1.5 millimeters. Next, they ask for the wavelength. So the wavelength is from here to here, and we have to look at what is that distance, right? And that wavelength is going to be given by 8 centimeters, because there's your 8. Next, they ask for the speed. So in 0.2 seconds, we go from this graph to this graph. So we have to decide how far something went. I'm going to use this crest. So this crest here went from being here, and then 0.2 seconds, now it's here. So it moved along from here to here. And since it moved from here to here, we can estimate that number, and it's like 3.2, be careful, centimeters. So 3.2 times 10 to the negative 2 is how far this peak moved to the right. And then that is its, went from here to here. That gives us our velocity, our velocity, because we know how far it moved, and we know the amount of time it took because it was from 0 up to 0.2 seconds. So we can take that distance divided by 0.2 seconds. And I think we get V from that being about, 32 divided by 0.2, so like 0.16, something like that, meters per second. And now we have the velocity. And so that helps us out there. What else did we know? We also knew the wavelength was 8 centimeters. And so that would be 0.08 meters for the wavelength. And so the last question asks for the frequency. But we know that velocity is frequency times wavelength, which tells us that thus the frequency is going to be the velocity divided by the wavelength. And so we can take the 0.16 divided by the 0.08, and we get the frequency of about 2 hertz. And so that's for part A, which I'm going to go ahead and stop.